4 years of education, thousands of hours of classes, hundreds of assignments, dozens of textbooks, mountains of information, and I remember almost none of it. Maybe 5%, maybe less, disappeared within months of graduation, gone, wasted. Perfai, hold up the thin notebook. This notebook represents everything Richard Feynman learned one summer when he was 15, just 3 months. Self-directed study, no classes, no teachers, just him and some books and curiosity, and he remembered all of it. Perfectly for his entire life. Could apply it decades later. Could teach it. Could build on it. It never disappeared. To put notebooks down, what's the difference? Why does one approach create temporary storage that evaporates, while the other creates lifetime memory that never fades? Our direct address, the difference is one rule. One simple rule that Feynman discovered at 15 and used for the rest of his life. A rule so powerful that everything learned using it becomes permanent. A rule so simple you'll think it can't possibly work. But it does work. It worked for Feynman for 70 years. It's worked for every person who's discovered it. And it will work for you. The balloon insert today. I'm going to reveal that rule, show you exactly what it is. Prove why it creates lifetime memory, and teach you how to use it starting immediately. Because right now, you're probably learning things that will disappear. You're investing time and effort into knowledge that won't last. You're filling your brain with information that will evaporate within weeks. And once you learn this rule, once you start applying it, that stops. Everything you learn from that point forward becomes permanent, lifetime memory, knowledge that never fades. Fire walk across stage. Let me start with the story of how Feynman discovered the rule. It's 1933. Feynman is 15 years old, summer vacation, and he wants to learn calculus. Not because he has to, because he's curious, so he gets some calculus books, goes to his room, and starts teaching himself. Fact, build the scene. No teacher, no class, no curriculum, no assignments, just him, the books, and a notebook where he works out problems. And something interesting happens. Something different from every other learning experience he'd had in school. He's not just reading the books. He's not just taking notes. He's not just solving the assigned problems. He's doing something completely different. Per reveal what he's doing, he's recreating calculus, rebuilding it from scratch. Not memorizing what the book says, but working out for himself why it's true, how it works, where it comes from. Every concept he derives himself. Every formula he rebuilds from first principles. Every problem he solves without looking at the solution first. Our share his approach. The book says the derivative of x squared is 2x. Feynman doesn't just memorize that. He works it out, okay? If I have a function x squared, and I want to know how fast it's changing, I need to see what happens when x increases by a tiny amount. So, x plus a minus esta divided by h. That expands to, let me work this out, 2x plus. And as h gets tiny, that approaches 2x. So that's where 2x comes from. I could make the distinction. He's not learning what the derivative is. He's discovering it himself. Not absorbing information. Creating understanding. Share the result. End of summer he knows calculus. Really knows it deeply. And that knowledge never fades. 40 years later, 50 years later, 60 years later, he still has it. Perfectly. Because he didn't just learn it. He created it. Reveal the rule I. That's the rule. That's the one thing that creates lifetime memory. Thas or never accept anything you can't derive yourself. Pause and pause. Let it land. That's it. That's the rule. Simple, obvious even, but profound and completely opposite to how most people learn. She explained the rule. The rule means don't just accept that something is true. Work it out yourself. Derive it. Prove it to yourself. Understand where it comes from and why it must be that way. If you can't derive it yourself, you don't really know it. You've just memorized someone else's conclusion, and memorized conclusions disappear. Self-derived understanding lasts forever. I fast make the contrast traditional learning. Here's a fact. Memorize it. Here's a formula. Use it. Here's a concept. Accept it. Passive reception. Someone else did the thinking. You're just storing their conclusions. Result temporary memory. Fades fast. Gone within weeks. Show Feynman's approach. Feynman's learning. Here's a fact. Why is it true? Let me work that out. Here's a formula. Where does it come from? Let me derive it. Here's a concept. How do I know it's right? Let me prove it to myself. Active creation. You do the thinking. You build the understanding. Result lifetime memory. Never fades. Permanent. Acts present the mechanism. Why does this work? Why does deriving create lifetime memory while accepting creates temporary storage? The neuroscience is clear. Your brain remembers what it creates far better than what it receives. I explain. When you derive something yourself, when you work it out, struggle with it, figure it out, your brain builds strong, multi-connected memories. The struggle creates the memory. The process creates the permanence. But when you just accept information, when someone tells you and you believe them, your brain creates weak, isolated memories. No struggle, no process, no permanence. Make it concrete, you're toldy. The area of a circle is arid, varid, easy. But it's just a fact floating in your memory, weakly connected, easily forgotten. Show the alternative, you derive it yourself. Okay. A circle is like many thin concentric rings. Each ring is basically a rectangle if I unwrap it. Width is 2 ver, thickness is jutra, area is 2 or 2 g dra. Sum up all the rings from 0 to r. That 2 bar jar from 0 to r, that's arm. That's where it comes from! Now you know it, really know it, and you'll never forget it. Because you created it, you struggled through it. You built the understanding yourself. Reshare the principle, self-created knowledge is permanent. Received knowledge is temporary. That's not motivation, that's neuroscience. Sex present the applications. So how do you apply this rule? How do you derive everything yourself? How do you create instead of just accept? Let me show you the specific practices, the ways to implement this rule across different types of learning. X practice 1, X practice 1. Derive all formulas. This is the clearest application. Any formula you encounter, math, physics, chemistry, economics, derive it yourself before using it. Make it concrete. Physics gives you kinetic energy equals 1/2 mv dio. Don't just accept it, derive it. Energy is force times distance. Force is mass times acceleration. Acceleration is change in velocity. So let me work this through. If something accelerates from 0 to v, the average velocity is v2. The distance is vg2 times t, but a is vt. So let me be more careful. Work it out. Get stuck. Figure it out. Until you can derive mv dive from first principles. Share the benefit. Now you own that formula. It's yours. You created it. You'll remember it forever. And you understand what it means, not just what it equals. I give Feynman example. Feynman derived everything. Every formula in his physics education. He worked out himself. If he couldn't derive it, he didn't consider himself to know it. That's why his knowledge was so deep, so permanent, so usable. Because it was all self-created, a practice 2 prove all claims. Any factual claim you encounter, in textbooks, lectures, articles, don't just accept it. Prove it to yourself. Work out why it must be true. And make it concrete. Biology textbook. DNA is a double helix. Don't just accept that. Why is it a double helix? What's the evidence? How do we know? Research it. Find the actual experiments. Understand the X-ray crystallography. Work through the logic that led to that conclusion. Convince yourself it's true. First, share the benefit. Now you don't just know DNA is a double helix. You know why we know that. You understand the evidence. You've followed the logic yourself. That's permanent knowledge. That's lifetime memory. Ask, give another example. History. The Treaty of Versailles contributed to World War II. Don't just accept it, prove it to yourself. What were the actual terms? What did they do to Germany? How did that create conditions for Hitler's rise? Work through the causal chain yourself. Now you understand it. Not just as a fact to memorize, but as a conclusion you've reached yourself. Practice 3, reconstruct all processes. Any process you're learning, how cells divide, how engines work, how the internet functions. Don't just read about it. Reconstruct it yourself from first principles. Make it concrete, learning how photosynthesis works. Don't just read the steps and memorize them. Start from first principles. Plants need energy. They get it from sunlight, but sunlight is energy in the form of photons. They need energy in the form of chemical bonds. So they must be converting photon energy to chemical bond energy. How would that work? What's needed? They work it out, piece by piece. Figure out what must be happening. Then check your reconstruction against what the textbook says. Share what happens. Where you got it right, that knowledge is now permanent. Where you got it wrong, you discovered a gap in your understanding. Fix that specific gap. Either way, you're creating understanding instead of just receiving information. Give Feynman example. Feynman learning biology. He didn't just read about cellular processes. He tried to figure out how they must work. what the logic must be, what the mechanisms must be. Then he'd check his reasoning against the textbook. That active reconstruction created deep, permanent understanding. At practice 4, solve before seeing solutions. Any problem, math, physics, coding, logic, try to solve it yourself before looking at any solution. Really try. Struggle with it. Even if you get it wrong, I can explain why the struggle is what creates memory. The process of working through it, getting stuck, trying different approaches, that creates permanent knowledge. Looking at a solution and understanding it creates temporary familiarity. Solving it yourself creates lifetime memory. Make it concrete math problem. Find the maximum of this function. Don't look at the solution. Don't even look at hints. Try to solve it. Maybe you remember calculus. Take derivative. Set to 0. Maybe you don't. Try graphing it. Try different values. Try reasoning about it. Spend real time. Struggle with it. Even if you don't get it, continue then, and only then look at the solution. Compare to what you did. Understand where you went wrong, or where you went right. Now you own this problem. You struggled with it. You thought about it deeply. You'll remember it forever. Richard Feynman's approach of Feynman never looked at solutions before trying problems himself. Never. Even if it took hours. Even if he got it wrong. The struggle was the learning. That's why his problem-solving ability was so strong. Every problem he'd solved, he'd really solved himself through struggle, creating permanent capability. Practice 5, explain before checking. After learning anything, explain it to yourself, sigh out loud, before checking any notes or materials. Build the explanation entirely from what you've created in your own understanding. URs make it concrete. Studied quantum mechanics. Close all materials. Explain quantum mechanics out loud. From what you understand, you'll get stuck. You'll find gaps. You'll realize parts you thought you understood but don't actually. Those gaps, that's what you need to derive yourself. Go back, not to memorize those parts, but to derive them, to work them out yourself until you can explain them. Often share the benefit. This practice reveals what you've truly created versus what you've just absorbed. What you can explain from your own understanding is permanent. What you can't explain is still someone else's knowledge, not yours. Bring practices together. So those are 5 practices for applying the rule. Derive all formulas, prove all claims, reconstruct all processes, solve before seeing solutions, explain before checking. Make the promise to use these practices and everything you learn becomes permanent. Lifetime memory, knowledge that never fades. Tell transformation story. Let me tell you about someone who discovered this rule. Call him Marcus. Marcus was in medical school, drowning thousands of facts to memorize. Anatomy, physiology, biochemistry, pharmacology, mountains of information. And he couldn't remember any of it. Study for an exam, pass, forget everything 2 weeks later. Constant cycle. Exhausting, frustrating. The crisis, 3rd year. Clinical rotation, needed to actually know medicine. Not just pass tests, actually know it, use it, apply it. He didn't. Everything he'd learned was gone. Had to constantly look things up. Couldn't reason through problems because he'd memorized instead of understanding. The discovery, then he learned about Feynman's rule. Never accept anything you can't derive yourself. And he thought, how do I apply this to medicine? His experiment, he picked one system, cardiovascular. And he decided, I'm going to derive everything myself. Not memorize how the heart works. Derive why it must work that way, what the logic is. What the necessary components are. First, his process started from first principles. The body needs oxygen. Oxygen is in the air. Cells are throughout the body. So there must be a system to move oxygen from air to cells. What would that require? Pump. Tubes. Distribution system. Return system. Let me think through what the design must be. Worked it out. Piece by piece. Why 4 chambers? Why valves? Why 2 circuits? Derive the logic, the necessity, the design. Within biochemistry. Don't memorize the Krebs cycle. Derive why cells must do something like the Krebs cycle. Cells need energy. They get it from glucose. But glucose is a molecule. Energy is stored in chemical bonds. So cells must be breaking glucose bonds and capturing that energy. How would that work? What steps must exist? Work it out. Build the logic. Derive the necessity. Then check against the actual Krebs cycle. And the transformation of 2 months into this approach, different student. The information stuck. The understanding was deep. The knowledge was permanent. Because he'd created it. Not just absorbed it, he owned it. Has the result had graduation top of his class. Not because he'd memorized more, because he understood deeply. And understanding doesn't fade. Decade later still has it. Still can reason through medical problems. Still can derive the logic. Because self-created knowledge is lifetime knowledge. Make the universal point. That's available to you. That permanence, that depth, that lifetime memory. Not by memorizing better, by deriving instead of accepting. Haxel addressed the objection now. Some of you are thinking, but I don't have time to derive everything. That would take forever. I have exams to pass. I need to cover material quickly. I can answer directly as are, yes, deriving takes more time initially, more effort, more struggle, but memorizing takes infinite time because you have to keep rememorizing, keep reviewing, keep studying the same material over and over because it keeps disappearing. And make the math. Derive something once maybe takes 3 hours, but then you have it forever. Total time investment 3 hours. Memorize something maybe takes 30 minutes, but then you forget. Rememorize before the exam another 30 minutes. Forget again. If you need it later, rememorize again another 30 minutes. Total time investment. Hours and hours and hours spread over years. Make the point deriving is front-loaded effort. Memorizing is infinite ongoing effort. Deriving is more efficient in total time. Second objection, but what if I can't derive it? What if I'm not smart enough? What if I get stuck? If I answer if getting stuck is the point, that's where learning happens. That's where understanding is created. When you get stuck, you've found the edge of your understanding. That's valuable information. That shows you exactly what you need to learn next. In fact, make it practical, get stuck deriving something, great. Now, you know what you don't understand yet? Go learn that specific thing, then come back and try again. That targeted learning is far more efficient than trying to learn everything just in case. I should give Feynman perspective. Feynman got stuck constantly, all the time. That's why he learned so much. Each time he got stuck, he found something he didn't know yet. Learned it, derived it, added it to his understanding. Getting stuck isn't failure. Getting stuck is the mechanism of learning. Vice present the deeper truth. Here's the deeper truth about why this rule creates lifetime memory. When you derive something yourself, you're not just storing a conclusion. You're building a web of understanding. Multiple pathways. Multiple connections. Deep integration. Explain is memorizing a Formula 1 fragile connection. This equals that. Break that connection and the knowledge is gone. Deriving a formula dozens of connections. This comes from that, which relates to this other thing, which I can see in this context, which connects to this principle I already know. It's a make the comparison. It's like the difference between remembering a phone number and knowing where someone lives. Phone number, arbitrary digits, fragile. Forget one digit and it's useless. Address, they live 2 streets over from the park, in the blue house, next to the bakery. Multiple cues, multiple connections. Even if you forget the street name, you can reconstruct it from the other information. Car applied 4 years of education, thousands of hours of classes, hundreds of assignments, dozens of textbooks, mountains of information, and I remember almost none of it. Maybe 5%, maybe less, disappeared within months of graduation, gone, wasted. Perfai hold up the thin notebook. This notebook represents everything Richard Feynman learned one summer when he was 15, just 3 months. Self-directed study, no classes, no teachers, just him and some books and curiosity, and he remembered all of it. Perfectly for his entire life. Could apply it decades later. Could teach it. Could build on it. It never disappeared. To put notebooks down, what's the difference? Why does one approach create temporary storage that evaporates, while the other creates lifetime memory that never fades? IFR direct address, the difference is one rule. One simple rule that Feynman discovered at 15 and used for the rest of his life. A rule so powerful that everything learned using it becomes permanent. A rule so simple you'll think it can't possibly work. But it does work. It worked for Feynman for 70 years. It's worked for every person who's discovered it. And it will work for you. So today, I'm going to reveal that rule, show you exactly what it is. Prove why it creates lifetime memory, and teach you how to use it starting immediately. Because right now, you're probably learning things that will disappear. You're investing time and effort into knowledge that won't last. You're filling your brain with information that will evaporate within weeks. And once you learn this rule, once you start applying it, that stops. Everything you learn from that point forward becomes permanent, lifetime memory, knowledge that never fades. If I walk across stage, let me start with the story of how Feynman discovered the rule. It's 1933, Feynman is 15 years old, summer vacation, and he wants to learn calculus. Not because he has to, because he's curious, so he gets some calculus books, goes to his room, and starts teaching himself. Fact build the scene, no teacher, no class, no curriculum, no assignments, just him, the books, and a notebook where he works out problems. And something interesting happens, something different from every other learning experience he'd had in school. He's not just reading the books. He's not just taking notes. He's not just solving the assigned problems. He's doing something completely different. Per reveal what he's doing, he's recreating calculus, rebuilding it from scratch. Not memorizing what the book says, but working out for himself why it's true, how it works, where it comes from. Every concept he derives himself. Every formula he rebuilds from first principles. Every problem he solves without looking at the solution first. Ours share his approach, eh? The book says the derivative of x squared is 2x. Feynman doesn't just memorize that, he works it out, okay? If I have a function x squared, and I want to know how fast it's changing, I need to see what happens when x increases by a tiny amount. So, x plus a minus esta divided by h. That expands to, let me work this out, 2x plus. And as h gets tiny, that approaches 2x. So that's where 2x comes from. I could make the distinction. He's not learning what the derivative is. He's discovering it himself. Not absorbing information. Creating understanding. Share the result. End of summer he knows calculus. Really knows it deeply. And that knowledge never fades. 40 years later, 50 years later, 60 years later, he still has it.
There is a lie about the double slit experiment that's told by everyone from famous physicists to YouTubers and even to believe it. The lie is, when you shoot electrons at two slits, if you don't watch which way they go, cruft, they'll act like waves. But if, you do watch which way they went, then, hey, act like particles. They go, straight through, and they end up in 2-bar lumps. This actually contradicts the results of the experiment, and it's completely the wrong lesson to take from he double slit experiment. But this Lieber has been told so often that it's kind of a life of its own. The real lesson this experiment is way more interesting. And I want to tell you about that. But first, let's find out what the electrons actually do when you serve them. Because it's not this Magina. We do have a bunch of articles like this that are going to craft this double slit experiment. You expect to have like 2 bunches of articles. And actually these slits are airy, narrow, and very close together. So, you'd kind of expect a bit of overlap between those 2 heaps. But here's what old happened for a wave. Okay, so I love his website because it's a wave emulator, and I'll link it in the description. But basically what we're owing here is we have this wall with 2 arrow slits, and we're going to see what happens when these waves go rough. So what you're seeing happen here is that there are these 2 A's coming from each of the slits. But when they touch each other, something weird happens. They interact with each other and kind of overlap. And if we let this go further, these interference patterns always kind of look like this, where there's a very strong bit of wave in the middle, and there's not much, and then there's more wave, and then again, there's a blank spot, and then another strong spot, etc. And as we saw in that simulation, what you'd expect for a wave is that it hits this back wall in this very funny pattern. There are some spots like this one where it's very intense, and then there are some spots like this where not intense at all. And there are these little bands of, intensity and no intensity. And when you do this experiment with light, that's exactly what you see, which suggests very strongly that light is a wave. In fact, the double slit experiment was the thing that really convinced people that light is a wave after all. And I've done the double slit experiment in a couple of videos before, and I always get a lot of comments being like, this is just classical optics, and that is true. But then they say, therefore, it's irrelevant to quantum mechanics, and that I disagree with, and I'll explain why a little bit later. But first, let's think about the same experiment with electrons. Is it going to turn out more like the particle case or more like the wave one? Well, this is footage from an actual double-slit experiment using electrons. So let's see what the answer is. Well, it's looking very promising for particles, because unlike with a wave, the result isn't just sort of smeared out. It's coming in these individual dots. But if we let the pattern develop, you start to see that it actually isn't in two lumps. It looks much more like the double-slit interference pattern for waves. So something really odd seems to be happening with these electrons. There seems to be some sort of wave associated with the electrons, and the wave spreads out. And just like a water wave or a light wave, it goes through both slits. The only real difference between an electron and a wave that goes through both slits is that the electron still ends up as dots. It isn't smeared out the way that waves usually are. But this feels wrong, because for something like light, I mean, it's perfectly fine to accept that it's some sort of wave. But for electrons, you know, we're used to thinking of them as little bullets like this, little particles. And a particle couldn't be going through both of these slits at the same time. That's why it's really natural to think that if electrons really are going through both slits, then maybe let's try and catch them in the act. Let's put two measuring devices here and here that will watch both of these slits, and we'll tell you whether the electron actually goes through both slits. The idea is that we want to be able to catch the electrons doing both things at the same time, but measurement in quantum mechanics doesn't work like that. So in quantum mechanics, when you try and measure an object, that's in a superposition of two different things like this electron going through both slits, then you will see a particular result. For example, this detector might see an electron go by. But now in quantum mechanics, what happens is that measurement changed the electron. Now it's only going through one of these slits, the one you observed. So far this is all correct. But here comes the myth. Many people will tell you that now that the electron has been measured, it becomes a particle. And so this particle will act like any normal particle, will sort of end up here. And so you can imagine that if we keep measuring which way every electron goes, then you end up with two piles of electrons. People will draw the results just like this as two clumps, or at most as two overlapping clumps. And so before I ever did these experiments myself, I assume that this is what happens, but that's not at all the case. And I'll get a curve that will probably look more or less like this. I wish I had experimental footage of someone actually doing this experiment with electrons to show you that this is not what happens, but I don't. And I also can't do this experiment myself, because working with the electrons is really hard. You need like a vacuum pump and everything, but the results that you get when you do the experiment with light are very, very similar. And so I did that experiment in my previous video, and this is the result that I got. What on earth is this crazy pattern? It doesn't look anything like two lumps. This is actually called the single slit interference pattern, and it's still very much wave behavior. Let me show you. So this is what the interference pattern looked like with the two slits here and here. But what happens if we take that away and instead just have one slit? So here I can change this from double slit to single slit, and let's see what happens. Okay, so it's much less distinct now, but you can still see some funny pattern going on here. So look, what happens at this bit where the slit is, you can see that there's like a funny sort of edge effect on both sides, and that edge, these two edges are what are going to interfere with each other. So the edges of that single slit interfere so that you get this kind of weird interference pattern. It looks quite similar to the double slit one, but just with like less fringes. So there's this bright fringe, and then dark fringe, and then a much less bright fringe and a dark fringe, etc. The single slit interference pattern looks something like this. But again, when we do this experiment with electrons, not actual waves, what we get is a slightly different pattern. We still get the electrons arriving in individual dots like this, but it's just that the dots are going to be according to this pattern. If you're wondering how this is different from the double slit experiment. Remember that there were all these little dips inside of the bigger single slit turn like this. So when you're not observing and you let the electrons go through both slits, then you get even more interference. But even when you just allow the electron to go through one slit by observing it, you still get a wave interference pattern. So what's going on? Well, let me tell you the correct explanation of the double slit experiment according to quantum mechanics. So for both light and for electrons, there is this thing called the wave function, which I've drawn here. It's the wave associated with that object. And when the two slits are open and not observed, the wave will go through both of those slits and interfere with itself. But in quantum mechanics, if you ever try and observe the position of an object, it can no longer be spread out like this. So when you do this observation, it forces the electron to collapse to just one of these. And so the electron acts like a wave even after it's been observed. And we know that because you end up with this single slit interference, which is just impossible to explain with purely particle behavior. If it's a wave, then shouldn't we expect a big smear across this wall rather than these individual particle-like things? Well, again, our measurement rule comes into play. In quantum mechanics, you can have an object that is spread out like a wave, but when you measure the position of that object, it's forced to collapse to a smaller position. So we have an electron that goes through here. When we measure it at the wall, it has to choose where to turn up, and it's going to be more likely to turn up in one of these bigger regions. So are electrons waves or particles? I think that even in this case where you're measuring the electron, it clearly acts in a way that's governed by this wave function. The wave is what determines what it does, but there is a sense in which it's particle-like. And that is because when it turns up on the wall, you'll find that there's always a full electron that turns up in any one spot. Like this electron has the same mass as that electron. So the fact that they arrive as these discrete and countable and always sort of the same size packages is what makes them particle-like. It's the fact that they can kind of be counted. And here's where it gets a bit weird. Light is exactly the same. In my previous videos about the double slit experiment with light, I got a lot of comments saying that the experiment that I was doing was just an experiment from classical optics, and all it showed is that light is a wave, which we've known for a long time. And that is all true, but I think that the quantum version of that experiment is not what people think. I got a lot of comments saying, why don't you do the single photon at a time version of this experiment? And the thing is, I would love to do that experiment, but I actually think it's going to be a little bit underwhelming, because basically this is how you would do it. Say that this is my source for the light. Then to do the single P photon at a time version of this experiment, all I need to do is to turn down this light. So I've just maybe put some filters in here that block the majority of the light. So there's only a little bit going through. Now our intuition tells us that if light is a particle, this thing called a photon, then surely it needs to be a particle like those little bullets that we were talking about. In that case, it would make total sense to talk about a single photon going through this experiment at a time. But that's not how light works. If I just put a filter in front of this laser, all I'm going to do is I'm going to make this wave weaker. From the side on view, the wave would look something like this, right? And as you put more filters in front, all that will happen is that the wave will get smaller and smaller. But no matter how many filters you put here, it's still a wave. At no point does it become a particle like this. And so you can see that no matter how weak these waves become, that doesn't stop them from spreading out like this. And the spreading is what really causes the double slit interference pattern. And so you still get the interference pattern. However, there is one really different thing about the result. Instead of getting a smear like you usually do with a double slit experiment, you're going to find actually the light arrives in little dots just like the electrons. But how is that possible? I said that nothing really changed when you turn down the intensity of this light. Well, the thing is, when we have This light at full brightness, there are individual dots turning up here, but we can't see them because there's so many coming per second that it does just look like a smear. And it's only by turning down the light that we end up seeing these individual photons. So photons are particles much like electrons are particles. They're not really, they're more waves. But a photon or an electron is more a property of what happens when they get measured. Whenever you have a quantum wave function like this and you try and measure the position of that object, it's forced to collapse to one particular spot. After I finished recording, I found out that there's this amazing paper where they explain how you can see the individual photons of light arriving. It is from 2016, and I'll link this in the description, but here's the video. So as you can see here, there are these individual photons, and it kind of looks random at first, but you can already start to see how it seems to be gathering around these fringes, which is exactly what you would expect for a double slit experiment. I'd seen this experiment with electrons before, but it was very cool to see it with photons. And as you can see, the two experiments look nearly identical. Another way that photons are very like electrons is that each individual photon has the same amount of energy as the other. Just like with electrons, they come in these discrete packages that are always of the same size. So for both electrons and photons, they don't really exist as particles. Throughout this part of the experiment, they only really become particles here when they're measured. But then you might wonder, how can we even talk about doing this experiment one photon at a time? Well, the way that you do it is you kind of turn down this light a whole lot so that there's only a few of these photons coming, let's say, every second. And it takes much less than a second for any light to have gone from the source all the way to the wall. And so you kind of say, well, that means that there couldn't have been more than one photon sort of going through this whole thing at a time. So that's a one photon at a time experiment. And I think that just is bad terminology. Like, there are no photons, really, until you get to here. For both electrons and photons, we imagine these as sort of individual balls coming out of the source. And that's what's the source of the confusion, because we think that a single particle can't go through two slits at the same time. But there is no contradiction when you see that both of them are actually just waves. And waves absolutely can go through both slits at the same time. They really only become particles when they're measured at the wall. That's why I think that experiments with light are still very interesting quantum mechanically, because we know from the maths of quantum mechanics that light and electrons behave almost identically. Like in my last video where I did the quantum eraser experiment with light, and it was very easy, and it just involved polarizers. A lot of people pointed out that you can totally explain this just using the regular polarization of light in classical optics. But did you know that you could do that exact same experiment again using the spin of the...
You think you understand gravity? Step on a scale. See the number. That's your weight. Earth pulling you down. Simple. Drop something, it falls. Moon orbits Earth. Planets circle the sun. Objects with mass attract each other. Newton figured it out centuries ago. The so-called force of gravity seems easy to understand. Simple even. Wrong. Not a little bit wrong. Fundamentally wrong about what's actually happening. Because gravity isn't a force at all. And when you finally see what gravity really is, when you really see it, the whole universe starts to look different. Let me show you. Stand up right now. Feel your weight. What are you feeling? You say, gravity, Earth pulling you down. But think about the actual sensation. The floor pressing against your feet, pushing up. That's what you feel. The floor pushing. This mysterious pull everyone talks about, you never feel it, not once. You only feel the push, always pushing up, never pulling down. So where's this pull? And here's something stranger. The moon is falling toward Earth right now, has been falling for billions of years, but it never gets closer, just circles, always falling, never landing. What kind of pull works like that? A pull that pulls forever, but never pulls anything in. And according to Newton, that pull happens instantly. Move Earth and the moon feels it immediately across 240,000 miles of vacuum, instantly. How? What carries the message? What's the mechanism? Newton himself couldn't explain it. He called it action at a distance and admitted he didn't understand how it worked. But the mathematics was beautiful. The predictions were perfect. So people stopped asking uncomfortable questions. They shouldn't have stopped. Go back several centuries. Nobody understood how planets moved. Copernicus said they orbit the sun. Fine. But how? What paths do they follow? Tycho Brahe built an observatory and spent decades recording planetary positions, night after night, year after year, measuring angles with brass instruments to fractions of a degree. Why such precision? Because you can't understand nature by guessing. You have to look. Measure carefully. Write down exactly what you see. That's where real science begins. His data reached Johannes Kepler. Kepler wanted to find the shape of planetary orbits. He tried circles. The predictions were close, but Mars was off by 8 arc minutes, 8/60ths of a degree. Most people would shrug that off as measurement error, but Kepler knew Tycho's precision. That man didn't make 8 arc minute errors. So Kepler threw out his theory and started over. After years of work, he found it: ellipses. Planets move in ellipses with the sun at one focus. Perfect match to the data. Beautiful. But it raised a bigger question. Why ellipses? Meanwhile, Galileo was doing simple experiments, rolling balls down ramps. Sounds trivial, but watch what happens. Roll a ball down an incline. It speeds up. Let it roll onto a flat surface. It keeps going, doesn't stop immediately. Now imagine you could eliminate all friction. What would happen? The ball would roll forever. Same speed, same direction, forever. This bothered people. Surely motion requires a continuous push. Surely things naturally come to rest. No, that's backwards. Motion is natural. An object moving in a straight line doesn't need explanation. That's the default state. What needs explanation is change. Slowing down, that's friction. Speeding up, that's a push. Changing direction, that's a sideways force. This is inertia, the first law of motion, and it creates a puzzle. Planets should move in straight lines. That's their natural state, but they don't. They curve. Their paths bend continuously toward the sun. Something must be deflecting them every instant. What? Isaac Newton saw it clearly. Planets want to go straight. That's inertia. But they curve. Something changes their motion constantly. He called it gravity. Universal attraction between any two masses. The force depends on mass and distance. More mass means stronger force. Greater distance means weaker force. Specifically, force drops with the square of distance. With this one principle, everything fell into place. Why ellipses? Because planets are falling toward the sun while simultaneously moving sideways. The combination creates elliptical paths. Kepler's laws emerge naturally from Newton's force law combined with inertia. Why does the moon orbit Earth? Same principle. It's falling toward Earth, but moving sideways fast enough to keep missing. It falls around Earth instead of into it. Why does an apple fall? Earth attracts it. Same force, same law, just different scale. Newton did a beautiful calculation. He figured out how much the moon falls every second, how much its path deviates from a straight line. Then he calculated how much objects fall on Earth's surface. The numbers matched perfectly when accounting for distance. Revolutionary. The force pulling an apple is the same force holding the moon in orbit. Heaven and earth, same physics. With Newton's law, everything made sense. Ocean tides happen because the moon pulls on Earth's water. Earth is round but bulges at the equator because it spins. Comets return on predictable schedules because they follow elliptical orbits. Strange observations found explanations. Jupiter's moon sometimes appeared early, sometimes late. Turned out light takes time to travel. When Earth is farther from Jupiter, light takes longer to reach us. This led to measuring light speed for the first time. Planets wobble slightly because they pull on each other, not just on the sun. From the wobbles in Uranus's orbit, astronomers predicted a new planet, Neptune, and found it exactly where predicted. For 2 centuries, Newton's law of gravity stood as one of the greatest achievements in science. It explained everything anyone could measure. But there was one detail nobody could explain. Drop a hammer and a feather in a vacuum. They hit the ground at the same time, exactly together. The hammer has more mass. So according to Newton, gravity pulls it harder, much harder. But the hammer also has more inertia. It resists acceleration more, much more. These 2 effects cancel perfectly, not approximately, perfectly. Every object falls at the same rate regardless of mass. Why? Newton's theory requires 2 different properties of mass. Gravitational mass determines how strongly objects attract each other. Inertial mass determines how hard it is to accelerate something. And these 2 properties are always perfectly proportional for every substance ever tested, to incredible precision. But why should the attracting property of mass and the resisting acceleration property be perfectly equal? Newton had no answer, just a remarkable coincidence that made the mathematics work beautifully. Or was it a coincidence? Einstein asked a different question. What if it's not a coincidence? What if that perfect equality is telling us something fundamental about what gravity really is? Here's a thought experiment. You're in a closed room with no windows. You feel your normal weight pressing you to the floor. Are you on Earth, or are you in a rocket in deep space, accelerating upward at 9.8 meters per second squared? Can you tell the difference? Drop something. It falls to the floor in both cases. Throw a ball horizontally, curved path in both cases. Stand on a scale, same reading in both cases. There is no experiment that can distinguish them. This is the equivalence principle. If you truly cannot tell gravity from acceleration, maybe they're the same thing. Maybe what we call sitting still in a gravitational field is actually a form of acceleration. Here's Einstein's revolution. Objects in free fall have no force acting on them. The falling apple, the orbiting moon, satellites circling Earth, astronauts floating in space capsules. None of them experience any force. They're moving naturally, following their natural paths. No forces, no pulls, nothing acting on them. But the apple is clearly falling. Yes, but what if the apple isn't accelerating at all? What if it's following the straightest possible path and it's space itself that's curved? This is Einstein's profound insight. Gravity is not a force between objects. Gravity is the curvature of space and time. Massive objects don't pull on other objects. They warp the space around them. They bend it, curve it, distort the geometry. The apple isn't being pulled to the ground. It's following the straightest possible path through curved space-time. But space-time near Earth is curved, so straight points toward Earth's center. You standing on the ground aren't being pulled down. You're trying to follow your natural path through curved space-time, a path toward Earth's center. But the ground is in your way. The ground pushes you upward, preventing you from following that natural path. That's what you feel as weight, not gravity pulling down. The ground pushing up, deflecting you from your natural trajectory through curved space-time. Einstein made a concrete prediction. If gravity is really curved space-time, then light should be affected too. Light has no mass. In Newton's theory, gravity shouldn't affect light at all. But if gravity is curvature of space itself, then light following the straightest path through curved space should bend. During a solar eclipse, astronomers measured the positions of stars near the sun's edge. The stars appeared displaced from their true positions. The starlight had bent, passing near the sun, exactly as Einstein predicted. This is gravitational lensing. We see it in observations all the time now. Massive objects bend light from more distant objects behind them, creating distorted images. Direct evidence that space itself curves in the presence of mass. Astronauts in orbit look weightless, floating around. Zero gravity up there, right? Wrong. The gravitational field at the altitude of satellites, a couple hundred miles up, is almost as strong as here on Earth's surface, about 90% as strong. So why do astronauts float? Because they're falling. The capsule is falling. Everything is falling toward Earth constantly. But they're also moving sideways very fast, about 17,000 miles per hour. As they fall, Earth's curved surface falls away beneath them. They keep missing. They fall around Earth instead of into it. Everything falls together at exactly the same rate. So there's no sensation of falling, no weight, no sense of up or down. It feels exactly like floating in empty space, far from any mass. This is equivalence in action. Free fall in a gravitational field feels identical to floating freely in empty space because they are the same thing. In free fall, no force acts on you. You're following the natural geometry of curved space-time. Think of Earth's surface. It's curved, but standing on it, it looks flat to you. And here's something remarkable. Why is Earth round in the first place? Because of gravity, but not in the way you think. It's not that some force is pulling everything toward the center, molding Earth into a sphere. It's that space-time around Earth's mass is curved equally in all directions. Every piece of rock, every drop of water is trying to follow the straightest path through that curved geometry. And when everything follows those curves from all directions equally, you get a sphere. The only shape where every point on the surface is the same distance from the center. Earth is round because that's what happens when matter follows curved space-time. The shape emerges naturally from the geometry. An ant walking what it thinks is a straight line on that curved surface actually follows a curve. But from the ant's perspective, it's going perfectly straight. That's what's happening with everything near Earth, except it's not just space that's curved, it's space and time together, space-time. Massive objects create curves in space-time, depressions, wells, distortions. The sun creates a deep well. Earth creates a smaller one. Even you create a tiny well, too small to measure easily, but it's there. Objects moving near these wells naturally follow the curves, not because anything pulls them, because they're following the straightest possible paths through curved geometry. The moon orbits Earth because it's following the natural geometry of curved space around Earth. That geometry makes the straightest path into a circle. An apple falls because it's following curved space-time near Earth's surface. In that curved geometry, straight ahead through time points toward Earth's center. When you throw a ball, it follows a parabola, not because gravity pulls it down, because it's moving through curved space-time, and the straight line in that curved space looks like a curve to you. You're standing light now. You feel weight. In Newton's picture, gravity pulls you down and the floor pushes you up. Two forces balanced. In Einstein's picture, only one force acts on you, the floor pushing up. But if there's only one force, you should be accelerating, and you are. You're accelerating upward constantly. The natural path through space-time points toward Earth's center. That's the free fall trajectory. But the floor is in your way. It pushes you upward, deflecting you from that natural path. You're like someone standing in an accelerating rocket. The floor pushes. You feel weight, not from any downward pulling force, from being accelerated away from your natural path. The apple hanging in a tree is also being pushed upward by the branch. When the branch breaks, the pushing stops. The apple is suddenly free to follow its natural path through curved space-time. It falls, but the apple isn't accelerating. The apple is finally free to move naturally. You standing on the ground are being constantly accelerated upward by the floor pressing against your feet. Falling is the natural state. Standing still requires a force. That's Einstein's revolution. Once you understand gravity as geometry, extreme phenomena make sense. A star is essentially a massive ball of gas. Its mass creates a deep well in space-time. The natural paths in that curved space point inward. What prevents collapse? Pressure from nuclear reactions in the core pushing outward. Balance. When the nuclear fuel runs out, the pressure drops. Balance breaks. The star collapses. If the star is massive enough, the collapse continues until matter is compressed to incredible density. Atomic nuclei merge. Electrons are crushed. What emerges is a neutron star. Nuclear matter compressed to city size. A teaspoon of this stuff would weigh 1 billion tons. For even more massive stars, not even neutron pressure can stop the collapse. Space-time curves so sharply that all possible paths lead inward. Even light cannot escape. This is a black hole. Near a black hole, space-time is so severely warped that light itself, following the straightest possible paths through this geometry, spirals inward and never comes out. We can't see black holes directly, but we see their effects. Matter falling toward a black hole speeds up, heats up, radiates enormous energy before disappearing. All from one idea. Mass curves space-time. Objects follow the curves. From this one principle, everything follows. Planetary orbits, tides, the precession of Mercury's perihelion, a tiny effect Newton's theory couldn't explain, but Einstein's predicts perfectly. Gravitational lensing, black holes, gravitational waves rippling through space when massive objects collide. The same principle explaining how the moon orbits also explains the largest structures we observe. Galaxies, clusters of galaxies, universal, elegant. The pattern in the small piece reveals the design of the whole fabric. Newton's equations work beautifully for practical purposes. We use them to launch satellites, calculate orbits, predict eclipses. They're simpler than Einstein's equations and accurate enough for most applications. But Einstein revealed what gravity actually is. Not a mysterious force pulling objects together across empty space. The curvature of space and time themselves. Mass tells space how to curve. Curved space tells objects how to move. When you step on that scale, you're not measuring a downward pull. You're measuring how hard the scale must push to prevent you from following your natural path through curved space-time. When you watch something fall, you're seeing an object finally free to follow the geometry that mass has woven into the fabric of reality. When you look at the moon, you're seeing an object following the straightest possible path through the curved space around Earth. a path that looks like a circle because space itself is curved. Space brings objects together. That's what we call gravity, not a force, geometry. And that is far more beautiful than any mysterious pull could ever be.
Let's begin by removing one dangerous habit from our thinking, the habit of believing something because it sounds exciting. Energy does not come from nowhere. It never has. It never will. If someone in the 1800s claimed they were pulling energy from the air, the correct response is not amazement. It is questions. What energy? Measured how? Compared to what? Under what conditions? Because nature is not impressed by our imagination. Nature only responds to experiments that survive measurement. Now here's the part most people miss. The 19th century was not a dark age of science. It was an age of raw curiosity. When people stuck wires into the sky, buried metal in the ground, spun magnets by hand, and asked absurdly bold questions. They studied atmospheric electricity. They observed potential differences between earth and air. They built devices that responded to electric fields long before modern power grids existed. Some of these experiments worked, some didn't, and many were simply abandoned, not because they were revolutionary, but because they were inefficient, unstable, or impractical. And here's the uncomfortable truth. When something truly works, people copy it. When it doesn't, it becomes a footnote. There is no global meeting where discoveries are erased. There is no secret vault where working physics is hidden. There is only one filter that matters: repeatability. You can find old patents. You can find strange machines and photographs. You can find notebooks filled with diagrams. That is evidence of curiosity, not proof of success. Proof requires this simple test. Can someone else build it and get the same result? If the answer is no, then the universe has already made its decision. But, and this matters, dismissing these ideas without examining them is just as unscientific as worshiping them. The correct position is uncomfortable. It requires discipline. You say, show me the measurements, show me the losses, show me where the energy enters the system. Because if energy were truly being harvested from ambient sources in a scalable way, we wouldn't need belief. We'd need extension cords. Science is not about protecting the status quo. It is about killing bad ideas quickly so good ones can survive. So the real lesson here is not that hidden energy was stolen from history. The real lesson is this: progress doesn't disappear. It either works and spreads or fails and gets forgotten. And our job is not to romanticize the past, but to question it correctly. That's how truth survives. Not by mystery, but by clarity. Energy is not magic. It is accounting. And the moment you forget that, you stop doing science and start telling stories. Every serious claim about energy begins the same way. You count what goes in, you count what comes out, and you explain the difference. No mystery, no poetry, just numbers that refuse to lie, even when we want them to. The universe keeps perfect books, and it does not forgive sloppy math. When someone says they pulled energy from the air, the sentence already contains a problem. Air is not a battery, it is a medium. It can carry energy, yes. Electrical potential, thermal motion, chemical gradients, but it does not give energy away for free. If energy appears to come from nowhere, it means you have failed to identify where it actually entered the system. Nature is not impressed by clever language. In the 1800s, people did not lack intelligence, they lacked instruments. They were surrounded by phenomena they could observe but not yet quantify with precision. Sparks jumped from metal, wires tingled when raised into the sky, needles twitched for reasons no one fully understood. These effects were real. The interpretations were often wrong. That is an important distinction most people ignore. When an experiment produces a result, it does not automatically produce an explanation. The result might be correct while the reasoning is garbage. History is filled with true observations wrapped in false theories. The danger is not that early scientists were foolish. The danger is assuming that because they were curious, they must have been correct. Energy accounting forces humility. It asks questions that are uncomfortable because they kill excitement. How much power is being produced? Over how much time? Under what conditions? With what losses? If the answers are vague, the claim is weak. If the answers change depending on who is asked, the claim is already dead. People love the idea of hidden energy because it suggests that reality has been cheating us, that someone somewhere cracked a code and the rest of the world was too blind to see it. But physics does not work like a secret society. It works like a public execution. If your idea is wrong, it is killed openly by experiment. In the 19th century, many devices appeared to generate energy from nothing. In almost every case, later analysis revealed a missing term in the equation. Energy was entering through temperature differences, chemical reactions, mechanical work. atmospheric electric fields, or simple human effort that went unnoticed. The machine didn't violate conservation. The observer violated careful thinking. This is why free energy is such a dangerous phrase. It invites people to stop asking where the energy comes from. It replaces investigation with hope, and hope is not a measurement tool. Real energy breakthrough does not need defenders. It does not need believers. It does not need dramatic music or warnings about suppression. It only needs replication. If a device works, other people will build it. If other people can build it, it spreads. If it spreads, it reshapes the world quietly and efficiently. That is how electricity won, not through secrecy, but through usefulness. There were no viral speeches announcing the death of candlelight. There were no accusations of global suppression. There were just better systems that made older ones obsolete. Progress does not ask permission. It replaces what fails. So when you hear that energy was once pulled from the air and then lost to history, the correct response is not belief or disbelief. The correct response is suspicion, directed equally at the claim and at our own desire for it to be true, because if energy could be harvested easily, cheaply, and continuously from the environment at large scale, the evidence would not be a dusty patent or a mysterious photograph. The evidence would be infrastructure. Cities would be built around it. Wars would have been fought over it. Economies would have reorganized themselves around it. Absence of that reality is not proof of suppression. It is a clue. The universe is brutally honest. It does not hide working ideas. It exposes them by allowing them to survive contact with reality. Anything that cannot pass that test does not get erased. It simply gets ignored. And this is the discipline that separates thinking from fantasizing. Energy accounting is boring to people who want miracles. It is unforgiving to people who want mystery. But it is the only language the universe understands. If you want to know whether something is real, stop asking who discovered it or why it was forgotten or who might have buried it. Ask a simpler, more dangerous question. Where did the energy come from? Exactly. If that question cannot be answered clearly, the idea is not revolutionary, it is incomplete. The 1800s were not primitive, they were experimental. And confusing those two is a mistake that poisons how people think about both history and progress. Primitive means lacking intelligence or curiosity. That was never the case. What they lacked was refined measurement, standardized theory, and the mathematical tools we now take for granted. But in exchange, they had something rare, the freedom to test ideas without knowing in advance what was impossible. They lived in a world where electricity was not yet tamed, where magnetism felt almost supernatural, where heat, light, and motion were still being argued over as separate forces or manifestations of the same thing. They did not inherit clean textbooks. They were writing them, often incorrectly, and correcting them through failure. That matters. Because experimentation does not require perfect understanding. It requires courage to be wrong in public. People in the 1800s built devices first and explained them later. Sometimes the explanation never came. Sometimes it came decades afterward, rewritten in a language that made the original inventor look naive. But the work itself was real. Sparks still jumped. Motors still turned. Fields still existed, whether anyone could describe them correctly or not. Modern minds often look back and see confusion. What they miss is momentum. These were people who raised wires into thunderstorms without knowing what would happen. They spun magnets by hand, listened to clicking relays, watched needles move, and refused to accept that these effects were meaningless. They suspected connections before equations existed to justify them. And that's where the danger begins for the modern storyteller, because an experiment that produces a real effect does not automatically produce a useful technology. Most of the time, it produces a dead end, not because the effect is false, but because it cannot be controlled, scaled, or made reliable. The history of science is not a straight line forward. It is a graveyard of clever failures. When people say they were doing things we can't explain, what they usually mean is they were observing phenomena we now understand better. The mystery is not evidence of superiority. It is evidence of incomplete models. Still, dismissing these experiments as primitive is just as foolish as worshiping them. The 1800s were an era where boundaries were porous. Physics, chemistry, engineering, and philosophy bled into each other. Someone could be wrong in theory and still right in practice. A machine could work for reasons no one correctly understood at the time. That is why you find devices in old texts that seem impossible by modern intuition. Not because they broke the laws of nature, but because modern intuition is trained on finished science, not raw discovery. Finished science is clean. Discovery is messy. They did not know which paths would collapse and which would become highways. They tested everything. Some ideas died because they violated reality. Others died because they were inefficient, fragile, or economically useless. A working principle that cannot survive real-world conditions is not a breakthrough. It is a curiosity. And here is the part people don't like hearing. Most abandoned ideas were not abandoned because they were dangerous or revolutionary. They were abandoned because something else worked better, quieter, cheaper, more predictably. Innovation does not need censorship to disappear. It only needs competition. The steam engine did not win because it was elegant. It won because it was controllable. Electricity did not spread because it was mysterious. It spread because it could be standardized. What survives is not what excites inventors, but what serves societies. So when you see an old experiment that appears brilliant but leads nowhere, the correct response is not to assume suppression. It is to ask why it failed to evolve. Did it require conditions too rare to maintain? Did it produce power inconsistently? Did it rely on environmental variables that could not be controlled? The people of the 1800s were not blind to value. They were ruthless pragmatists. If something worked, they used it. If it didn't, they moved on without sentimentality. This is what made the era experimental rather than primitive. They were willing to throw away ideas they loved when reality refused to cooperate. That discipline is rarer today than people think. Modern culture often confuses skepticism with closed-mindedness and curiosity with belief. The 1800s did not have that luxury. Failure had consequences. Time and materials were expensive. Nature decided quickly. The tragedy is not that some experiments were forgotten. The tragedy is that modern audiences resurrect them without understanding why they died. Respecting the experimental nature of that era means honoring both their curiosity and their errors. It means recognizing that progress is built on discarded attempts, not hidden miracles. They were not secretly ahead of us. They were bravely uncertain. And that uncertainty, tested relentlessly against reality, is what actually moves science forward. Pulled from the air is a comforting phrase. It sounds simple, generous, almost miraculous. And that is exactly why it is dangerous. The phrase hides ignorance behind familiarity. Everyone knows what air is, so the mind relaxes. It stops asking precise questions. But air is not a thing you pull energy out of. It is a mixture of gases, moving molecules, electric fields, temperature gradients, pressure differences, and chemical potential. When you say from the air, you are refusing to say which of those you mean, and refusing to be specific is not curiosity. It is avoidance. Energy does not float around waiting to be collected. It exists in particular forms, under particular conditions, and it only moves when there is a gradient, a difference that can be exploited. No difference, no flow. No flow, no power. That rule has never been broken, not once. So when someone claims energy was pulled from the air, what they are really saying is that they do not know where the energy came from. And ignorance is not evidence of novelty. In the 1800s, this confusion was understandable. Electric fields were invisible. Atmospheric charge was poorly measured. Temperature and pressure were difficult to quantify continuously. When a device behaved unexpectedly, the explanation often lagged behind the observation. Something seemed to come from nothing because the pathway was hidden, not because it was absent, but hidden is not the same as magical. If a wire raised into the sky produces a current, the energy is not coming from the air. It is coming from a potential difference between two regions of space. If a device responds to temperature changes, the energy is not coming from the air. It is coming from thermal motion. If a system produces power during a storm, the energy is not free. It is paid for by atmospheric dynamics on a planetary scale. Calling all of that air is like saying a city runs on buildings. It tells you nothing useful. The phrase also smuggles in a second error, the idea that availability implies usability. Just because energy exists in the environment does not mean it can be harvested efficiently, continuously, or at scale. There is energy in the ocean waves, in sunlight, in wind and heat differences between day and night. Yet capturing it requires infrastructure, materials, and compromises. No one calls a wind turbine a miracle. They call it expensive. Environmental energy is diffuse. That is the key problem people avoid. Diffuse energy is hard to collect because it does not want to move in one direction. You must build something that forces it to, and forcing nature costs energy of its own. This is where most pulled from the air stories quietly die. They work once or briefly or under special conditions. Then they fail when asked to deliver consistent power. The device didn't tap an infinite source. It exploited a temporary imbalance and then waited for it to return. When it didn't, the magic vanished. But the story remained, and stories are easier to spread than equations. Another problem with the phrase is psychological. It invites people to imagine a loophole, a way around limits, a bypass of conservation, a victory over constraints. But physics is not a courtroom where clever phrasing wins cases. You do not defeat conservation. Laws with enthusiasm. Every serious energy system, no matter how advanced, answers the same brutal questions. Where is the gradient? How fast does it replenish? What is the maximum extractable power? What happens when many people try to use it at once? If those questions are not answered, the system is not revolutionary. It is incomplete. This is why historical devices must be treated with discipline, not reverence. If a machine truly pulled usable energy from the environment in a scalable way, the phrase "from the air" would never survive scrutiny. Engineers would replace it with diagrams, equations, and performance tables. Vagueness would be a liability, not a feature. The persistence of the phrase is itself evidence of failure. It survives because nothing precise replaced it. That does not mean those inventors were foolish. It means they were exploring phenomena before language and theory caught up. Some of what they observed later became mainstream science. Most of it didn't, not because it was suppressed, but because it could not deliver what society needed. Precision is the enemy of fantasy. The moment you demand specificity, most myths collapse under their own weight. So when you hear that energy was pulled from the air, do not argue, do not mock, do not believe, ask a sharper question. Which energy? Which mechanism? Which gradient? Which limits? If the answers dissolve into metaphor, the idea is already finished, not because it is forbidden, but because it is undefined, and anything undefined does not power the world. Suppression is the explanation people reach for when they do not want to face a harsher possibility that the idea simply wasn't good enough. It sounds dramatic. It assigns blame. It flatters the believer by casting them as someone who sees what others were too afraid to acknowledge. But in most cases, suppression is not a historical reality. It is an emotional shortcut. Neglect is quieter, less satisfying, and far more common. Most ideas do not die because someone kills them. They die because no one picks them up again. They fail to justify the time, money, and effort required to keep them alive. There is no villain in that story, and that is precisely why people resist it. History does not erase working systems. It absorbs them. If something produces reliable energy, people use it. If people use it, it spreads. If it spreads, it becomes infrastructure. You do not need permission for that process. You do not need consensus. You only need results. This is why the suppression narrative collapses under basic pressure. To suppress a technology that genuinely works, you would need global coordination across rival governments, competing industries, and hostile ideologies, all agreeing to lose power, wealth, and advantage for the sake of secrecy. That level of cooperation does not exist even when the stakes are survival. People cannot agree on lunch. They do not conspire flawlessly against progress. What actually happens is far less theatrical. A device works under narrow conditions. It fails outside the lab. It degrades. It scales poorly. It costs too much. It requires maintenance no one wants to perform. It solves a problem that turns out not to matter, so it gets ignored. And then, decades later, someone rediscovers it without understanding the context of its failure. They see the promise, but not the limitations. They mistake abandonment for censorship. This is not malice. It is misunderstanding. The industrial age was brutally pragmatic. Investors did not care about elegance. Governments did not care about beauty. They cared about output, reliability, and control. If an energy system could not deliver those, it did not survive. There were no committees tasked with burying breakthroughs. There were accountants deciding what was worth funding. And accountants are far more effective at killing bad ideas than conspirators. Neglect does not require intention. It only requires indifference. An idea that fails to attract builders, refiners, and maintainers fades naturally, not because it threatens power, but because it does not create enough of it. People underestimate how hard it is to keep a technology alive. A working prototype is not enough. It must survive manufacturing, training, repair, supply chains, regulation, and competition. Most ideas fail long before they reach those gates. Calling that suppression is an insult to reality. It also reveals a deeper problem: the need to believe that truth is persecuted. This mindset replaces evidence with grievance. It trains people to defend ideas instead of testing them. And once an idea becomes part of someone's identity, it stops evolving. Neglect, on the other hand, is mercilessly honest. It does not argue. It does not explain itself. It simply withholds attention. The universe works the same way. Bad ideas are not punished. They are ignored. They do not trigger alarms. They do not provoke resistance. They just fail to propagate. If a technology truly threatens existing systems, it does not disappear. It gets adopted, stolen, improved, and weaponized. History is full of examples. Superior tools do not stay hidden. They become unavoidable. The absence of widespread adoption is not suspicious. It is informative. This does not mean institutions are benevolent or wise. It means they are opportunistic. They absorb anything that gives them leverage. If they didn't absorb it, it likely didn't deliver. This is an uncomfortable conclusion because it removes the romance. It suggests that many lost ideas were not ahead of their time, but trapped by it, unable to mature because they could not meet real-world demands. And that is not a tragedy. It is the cost of progress. Understanding this forces intellectual responsibility. You cannot hide behind claims of suppression to avoid hard questions. You must ask why the idea failed to scale, why it lacked resilience, why it could not compete. Neglect is not an insult. It is a verdict, and unlike suppression, it does not require a story. It only requires silence. So when someone claims a breakthrough is buried, the correct response is not outrage. It is analysis. What problem did it solve better than alternatives? Who tried to use it? What happened next? If the answers are vague, emotional, or circular, the explanation is already clear. Not everything forgotten was stolen. Most of it was simply left behind. That evidence exists. That is not the question. The question is whether it proves what people think it proves. A photograph is evidence. A notebook is evidence. A patent drawing is evidence. A strange device in a museum case is evidence. But none of these things by themselves prove that a claim about energy, physics, or technology is true. They only prove that someone believes something strongly enough to record it. Proof is a higher standard. Proof demands performance. This distinction is where most people lose discipline. They collect artifacts the way others collect souvenirs and then treat accumulation as validation. But reality does not care how many documents you have. It cares whether the system works when someone else builds it. The history of science is full of confident documentation that led nowhere. People wrote extensively about perpetual motion. They filed patents. They built models. They defended them passionately. None of that made the machines real. It only made the mistake well documented. Evidence shows intent. Proof shows truth. This is why laboratories exist. This is why experiments are repeated by people who have no emotional investment in the outcome. Science advances not by loyalty to ideas, but by betrayal of them. A theory earns respect only by surviving attempts to destroy it. When someone points to old diagrams or blueprints and says, "Look, they knew something," the correct response is not dismissal or awe. It is interrogation. Did it run? For how long? Under what conditions? With what inputs? And what happened when those conditions changed? If those questions cannot be answered, the evidence has reached its limit. There is also a subtle trap here. People confuse originality with correctness. An idea being unusual does not make it right. In fact, most unusual ideas are wrong. What makes an idea valuable is not how different it is, but how well it matches reality. The universe does not reward creativity. It rewards accuracy. A device that works once is evidence of a phenomenon. A device that works reliably is evidence of understanding. A device that others can reproduce is evidence of truth. Each step is harder than the last, and most claims die along the way. That is not injustice. That is filtration. Old patents are often misunderstood in this context. A patent does not certify that something works. It certifies that someone described an idea in sufficient detail to claim ownership if it ever does. Many patents are never built. Many that are built fail. The existence of a patent proves paperwork, not physics. Similarly, written accounts must be treated carefully. People misinterpret results. Instruments drift. Measurements are flawed. Observers see patterns that vanish under better controls. The past is not immune to error just because it is distant. Respecting history means acknowledging that intelligent people can be wrong. Evidence without context is dangerous because it invites projection. Modern minds look backward and insert meanings that were never tested. They see what they want to see, not what was demonstrated. Proof resists that temptation. Proof is boring. It does not care about narrative. It demands numbers, tolerances, failure modes. It asks what breaks first and why. It survives criticism because it has been shaped by it. This is why science moves slowly and mythology spreads quickly. The existence of forgotten experiments does not imply lost knowledge. It implies unresolved questions. And unresolved questions are not treasures. They are invitations to work. If the evidence were enough, the work would already be done. People often say the evidence is there if you look, but that sentence reveals the problem. Proof does not hide. It announces itself by changing the world. When something works, people notice without being told where to look. Electric lighting did not require persuasion. Neither did engines, radios, or antibiotics. Their success was visible in daily life. They did not need defenders. They needed sockets. So when evaluating claims about historical breakthroughs, the burden of proof does not lie with skepticism. It lies with performance. If an idea cannot be rebuilt and tested today using the same principles, the evidence remains incomplete. That does not mean the idea is false. It means it is unfinished, and unfinished ideas belong in laboratories, not legends. The mature position is neither belief nor denial. It is restraint. You acknowledge what exists without pretending it means more than it does. You separate curiosity from conclusion. You allow evidence to guide questions, not dictate answers. That discipline is uncomfortable. It removes certainty. It denies closure. But it is the only posture that keeps thinking honest evidence exists. That is easy. Proof must be earned.